Okay, so our next speaker is Nick Harris, founder and CEO of Lightmatter. Nick is MIT-trained engineer and scientist. He won the MIT Technology Review's TR35 award and holds numerous patents on revolutionary photonics technologies. As I mentioned in my welcome speech, Nick has delivered a very impactful keynote in 2023 on light matter passage, and I'm looking forward to hear his updates right now. So Nick, stage is yours.
All right, great to be back and excited to tell you guys what we've been up to at Lightmatter. Um, I always enjoy the Hot Interconnects event. So today we're going to talk about transforming AI infrastructure with 3D photonics. Just to zoom out for a quick second here, I think it's interesting to think about the reality of how big these machines we're building, how big these machines are we're building for computing. They consume, gigawatts of power. They're getting closer and closer to the scale of the largest cities on Earth. And in order to make that kind of machine run, you need incredible interconnect technologies. But interconnect progress is really too slow. This is data over the past couple of decades looking at the rate of progress in compute measured in floating point operations per second, not necessarily floating point at this point, precisions are quite low, versus interconnect. And this is looking at optical interconnects and electrical interconnects. There's a huge gap between the rate of progress in compute and interconnect. And we need to close that because machines are starved for data. They're basically waiting for results, and that doesn't help us get to AGI and advancing the AI initiatives at the rate that we would like. So one of the central challenges in trying to close that gap is that communication between chips happens on the perimeter of the die. It's on the ring around the outside of the die. That ring around the outside of the die is called shoreline, and there is not enough shoreline. The area of the chip grows, quadratically with length, and the chip perimeter is linear with length. So the bigger computer chips get, the worse this problem of communication bottlenecking gets. And we need to get to about 100x the bandwidth of the chips that are out there today. And we need to get to much higher radix because it flattens networks, allows us to build bigger, faster, more performant supercomputers. But there's this unfortunate challenge, which is that radix and bandwidth compete for shoreline. So a new paradigm is needed, and excited to tell you about what we're doing. Before I jump into this video, I think it's important to sort of note that today people are using copper to do scale-up networking, and it's like taking two racks and pulling them together as tight as you can with copper shoelaces, and trying to use that as your scale-up domain. That's going to happen this year and next year. And these little mini brains are linked together with low speed, pluggable, detachable sort of interconnect technologies, 800 gig going to 1.6 T. And that's really not going to be sufficient. We need much larger scale up domains. Let me move on here. So what does it take to build a single brain million XPU data center? The challenges we have to solve is copper can only lace about 100 chips together. There's not enough chip shoreline to achieve the kind of bandwidth and radix that we need to build these AI supercomputers, and we need significantly more bandwidth, 100x. So the next 1000x in compute performance is going to come from photonics, and I'm here today to tell you that that technology is here and ready. If you look at what's out there in the interconnect space today in terms of optics, the industry is really looking at pluggables 17 to 20 picojoules per bit. That means every terabit's about 17 watts. People are working on NPO, so everyone's trying to get to this near package optics or package on package optics. These are around 8 to 15 picojoules per bit. After that would be 3D CPO. And what we do at Lightmatter is 3D stacking. Rather than having chiplets around the outside on the shoreline, we 3D stack processors, switches, ASICs on top of our photonic technology passage. And this is the ultimate limit on how fast, how energy efficient you could possibly be. And we have two types of passage technologies. There's our L series. These are 3D CPO engines, IO tiles, 3D stacked on top of passage. And we have our M series. M series is taking the entire switch or GPU or ASIC complex and 3D stacking it on top of our photonic interposer. And available 26 for L series, and next week we'll share a lot more about Passage M series. So I want to share really briefly some results that we just had, and I'm going to get into some gory technical detail. So we've just announced the world's first 16 wavelength bidirectional link. So 16 wavelengths, each optical fiber carrying 800 gigabit per second. That's an entire pluggable transceiver on one fiber. Bit error rate better than 10 to the minus 10 without forward error correction, so way beyond the Reed-Solomon threshold. 2.6 picojoules per bit for the Photonics and 2 picojoules per bit for the SerDes. We don't build SerDes. We work with our customers and use whatever they have there, but that gets you to 4.6 picojoules per bit. So we're already below 5 picojoules per bit, which is kind of a dream for the industry. This demonstration was shown over a kilometer of fiber with 3 dB channel loss, 6 connectors, polarization being tortured with a polarization shifting device. So our partners have been to the lab, seeing our rack scale validation platforms, and we're really excited to have this technology out there. And by the way, it's extremely temperature stable. So let's talk a little bit about our modulation technology. There are 3 technologies that people look at in the market: Mach-Zehnder modulators, or MZMs, EAMs, or electroabsorption modulators. They're made of germanium and silicon, or micro-ring modulators. So in Light Matter's technology, we use micro-ring modulators. They're about 10 times smaller than electroabsorption modulators and about 1,000 times smaller than Mach-Zehnder modulators. This drives density. Not only are they smaller, but they're lower power. If you look at the power required to drive Mach-Zehnder modulators, EAMs, and MRMs, you're at the absolute bottom of the range there in terms of the power consumed for driving these devices. So incredible power efficiency and spatial density. And they're incredibly thermally stable. So with Light Matter MRM control technology, we're able to show over temperature ranges of 0 to 105 C, rock solid performance in terms of link stability and everything else. And we can support both the C and O band with 5 dB transmit effective loss. And by the way, it's a multiplexer. Unlike Mach-Zehnder's and EAMs, you don't have to add a multiplexer. The modulator itself does the multiplexing. And the tech is backed by top foundries. Contrast this to EAM. They're thermally unstable. The data is shown there. There's no O-band support, 10 dB transmit loss, and it requires an external mux. And if you want to get to C-band support as well, you're going to need silicon germanium quantum wells, which are very exotic. So let's talk about the rock solid thermal data. Here's excursions, so bidirectional link, two chips talking to each other. 0 to 105, you can see the temperature in red. You can see the bit error rates in the lines on the bottom. So this is cycling from 25 to 105 to 25C over and over again across days. In this data, we're showing 0 to hour 30 minutes. Pretty incredible, rock solid. So let's take a look at what these MRMs actually look like. The diameter of this ring is about 15 microns. Here you can see the bit error rate bathtub curve, and on the right, another representation of this. You can see the tuning efficiency and the electro-optic bandwidth. They're really incredible devices, and they're extremely small. The transmit and receive circuits and the modulators all fit effectively in the area of a single bump. So we're 3D stacked, and we kind of fit everything underneath just the bump. And this is all powered by our guide laser. Each guide laser today is powering 32 terabits of optical I/O. Here you can see 16 wavelengths in a spectrometer and total power of around 3 watts. So at Light Matter, we're enabling multiple generations of the technology roadmap today. What I'm showing in the table here is all of the different modulation formats and link standards that we support, from 56 gig to 112 gig to 224 gig. We support both standards and custom advanced link technologies. So we're already at 800 gigabit per second and 1600 gigabit per second per fiber available today. And we invite partners to come leapfrog in this AI race with Light Matter. I'll just give a shout out to my co-founder Darius, who will be giving a talk at Hot Chips next week unveiling Passage M1000, which is truly a monster chip. All right, thank you.